Okay, so for uh, chapter 4, section 1, we're going to be dealing with probability distributions. And these probability distributions are going to come from the probability of a particular random variable being selected. Now, the first thing you have to do is understand what a random variable is. And it says that when you're dealing with a probability experiment, okay, you guys know what those are: flipping coins, drawing a card, reaching your hand in a bag and drawing a marble. Um, those are just some of the things that we've worked with, but it could be other things like doing a survey. Okay, so there's lots of different probability experiments. But when that probability experiment deals with something that we count or measure, okay, if we're dealing with anything that can be counted or measured, how many ice creams were sold during a particular period of time, the height of the people that we are surveying. These are things that you can count or measure. When you're dealing with a count or a measure, it's called, the outcome is called a random variable. And then here it just says we normally use the letter X to represent the random variable, or to represent the value associated with each outcome of the probability experiment. So if we said these, I'm asking, so here, I guess I should put a question mark here. This list of 7 things, I'm going to ask to see if it is a random variable now. If age is the outcome of whatever probability experiment that you're having, is age the ages that we collect? I don't know, 12, 15, 35, 53. These are some ages that you could collect. Would those ages be considered a random variable? So is an age something that you can count or measure? I hope that you're saying yes. It is a numerical value. It is something that you can count. Age is a count. And so, if age was the outcome of the probability experiment, then it is considered a random variable. What if gender, male, female, other? Is that a random variable? No, because we're not dealing with a numerical value. Hair color. Is hair color a random variable? No, because hair color is blonde, blue, brunette, red, gray. Those are not numerical values. Height, is that a numerical value? Or of something that is counted or measured? Is height counted? Is height measured? Height is definitely something that's measured. So yes, it would be a random variable. The number of children, if that was a question on a survey, how many children live in the household? And the answers to that question are your random variable. Or the answers to that question is what we're trying to determine: is it a random variable or not? Well, number of children, what's a possible answer? 0. Number of children, what's a possible answer? 1. Number of children, 3. Number of children, 2. My answers are numerical values. Those are children, are things that you count. So it is a random variable. A job title: teacher, nurse, doctor, principal, um, technician, hairstylist, colorist, anesthetician. That's a very hard word to say. Are those numerical values? Or is a job title something that you can count or measure? The answer is no. Number of hours on a transcript. That is a numerical value. That's something that you can count. So it's pretty easy to see which are going to be, so that we're going to be dealing with things that we can either count or measure when we're dealing with probability distributions for discrete random variables. Now we need to look at the 2 definitions that we need to know, and the 2 words are discrete or continuous. And up here they were talking about things that you can count. If you can count it, it is a discrete random variable. things that you measure, that is continuous. A continuous random variable. So if it's something that you can be counted, and generally the idea behind counting things, you cannot have a half or a portion of one. You can't have 2.5 phone calls. Notice there's no dot. There's a dot on 2 phone calls, or there's a dot on 3 phone calls. There's no dots in between because you can't have 2.5 phone calls. You just either have 2 phone calls or if you have 3 phone calls. This would be true if you were counting how many kids you could put on a bus. This could be true if you were counting the number of puppies in a litter of puppies. You're not going to have decimal values of things that you count. If I'm counting the number of ice cream cones sold during rush hour, okay, the number of ice cream cones is, you can't sell 2.5 ice cream cones. You're either going to sell 2 or you're going to sell 3. But things that you can measure, those are the things that are continuous. Height, weight, time, the number of hours that you spent on the calls. You can spend 3.5 minutes, okay, on a phone call. You can spend 2.5 hours on a phone call. You can be 6.5 feet tall. So notice that they have a dot right here at the beginning, that's 0 time, and then they have a dot all the way up here to 24 hours. So any amount of time in between there, and that's probably not a very good drawing, but they've got a solid dot here and a solid dot here, and then everything between here and here is shaded. And the shading represents that any of those values are possible. And it includes, since everything is shaded, that includes the decimal values in between the whole values. So that's the difference between discrete and continuous. Discrete is something that you cannot have a half of, or you wouldn't want to have a half of it, like 2.5 ice creams. Now, somebody would argue that I'd be totally okay with 2.5 cookies. If I have a broken M&M in my bag, I'm going to eat it. Yeah, if it's, so you have to be a little flexible here with things. Even though a cookie would be something that's considered discrete because you count cookies and there's no half cookies, we technically know that if you break a cookie, you can still eat the half. But anyway, the difference between whether you count it or whether you measure it, measured or weight or anything like that, that's continuous. No decimals, decimals are okay. No fractions, fractions are okay. So those are the 2 main differences. And then the next thing we're going to do real quick is I'm going to tell you that you need to know that a probability distribution must be a number between 0 and 1. So if they tell you that the probability that something is going to happen is 1.5, that is not possible, because it must be a number. Your probability of that discrete variable must be a number between 0 and 1. And then, as long as you get all numbers between 0 and 1, they're always going to add together to be 1. So with that definition in mind, this down here, now I don't know what the probability experiment was. I don't know what we did here to get a 5, 6, 7, or 8. Maybe it was a spinner, and on the spinner there was a slot marked 5, a slot marked 6, a slot marked 7, and a slot marked 8. And we spin the spinner. Maybe the spinner, obviously, if these are appropriate weights, then that means that the 5, the 7 spot right here was way bigger because it has a much bigger probability than landing on 5. So maybe there was 2 slots marked 7. But anyway, they want to know, even though I don't know what the probability experiment is, they want to know if this represents a good probability distribution based on these 2 definitions. Well, these are all numbers that are between 0 and 1. So they meet this condition. They meet condition number 1. 0.28, 0.21, 0.43, 0.15. Those are all numbers between 0 and 1, so that's fine. But do they add together to be 1? So if you add these up, I believe you come up with the sum of these probabilities is equal to 1.07. So this is not a probability distribution. And the reason it's not a probability distribution is because it added up to be, these probabilities right here added up to be more than 1. Probabilities have to add to be up exactly 1. What about this one? Is this, maybe this could be a four-sided triangle thingy that we roll, and it has numbers 1, 2, 3, 4 on the sides. I don't know, or it could be again another spinner. If it's not real easy to see the fractions right here, these are all actually, this one right here, that 5/4 is bigger than 1. 5/4 is greater than 1. That 5/4 is 1.25. So 1.25 is greater than 1, and this number right here is a number that's less than 1. Or it's less than 0. So it fails in two cases right here. It's a number that's less than 0, cannot have a negative probability. That's nonsense. That's like me saying, what flavor pizza would you like for me to order? And you say blue. Okay, blue is not an answer to what kind of pizza do you want. So -1 cannot be a probability of a random variable because it has to be a number between 0 and 1. This is not a possible answer. And 5/4 is a number it's an improper fraction, so that's definitely a number that's bigger than 1 all by itself. So even though it's a number that's bigger than 1, it can't belong to a probability distribution because each individual probability must be a number between 0 and 1. Now, this probability distribution may add together to be 1. I don't know. I believe it does. If you add all those up, I think you do get 1. But remember, both conditions have to be met. Okay, I'm going to stop this video here because it's a good time, and we'll pick up for the rest of the notes on the next video.